All right, hello everyone. My name is Brad Behrens. Today I'm going to talk about green propulsion in space, so specifically the Aerojet Rocketdyne GR1 and GR22. So I'm going to start off with describing the background on monopropellant thrusters. Then I'm going to move into looking at the Aerojet Rocketdyne GR1 and GR22 monopropellant thrusters and their new fuel that they use. And then lastly, I'm going to describe the NASA GPIM mission, which uses this new technology. So first of all, given background on these thrusters, there's a couple main purposes. One of the big purposes of these thrusters is a reaction control system where they do attitude control for spacecraft and satellites. In this case, you can see the schematic on the right where there's these thruster modules and they have pairs of thrusters for each axis so that they can either rotate the spacecraft or move it longitudinally. Additionally, these thrusters are used for flight velocity adjustments or changing orbits. And then they're also used with docking up with other spacecraft. And then in the case of various companies such as SpaceX, they also have thrusters on their launch vehicles. The goal of these thrusters is reliability so that they have high mission assurance when these missions are going many, many years, 15 years or more. So these thrusters, how they operate is by pulsing to create fine orientation changes of the spacecraft. And so you can see their duration of pulse is very short, within hundredths of a second. And then also their startup time is very short. And so there's a big trade-off between if you have a fine orientation change, that means your spacecraft thrusters are firing very short. And so most of that time is transient. And if it's transient, the chamber pressure is not as high. And so your ISP is going to be lower and your thrust is going to be lower. And so your efficiency is less. Um, these thrusters are also characterized by their duty cycle. So the total added up time of the pulses over the total flight duration. And usually this is pretty small number, so around 30% or less. So here's an example of thrusters on the first stage of a SpaceX rocket. You can see the cold gas thruster, and it's used to orient the rocket as it's coming down the land. Um, these are cold gas thrusters because it's purely just GN2 that's pressurized and it runs out through a nozzle and provides a small amount of thrust to orient the rocket. So now I'm going to talk about the monopropellant thrusters. They're called monopropellant because they use one fuel that runs through a catalyst bed, and the catalyst causes it to do its combustion or decomposition reaction. And in this case, there's a pressure feed system that pushes the fuel through the nozzle and the thrust chamber. Um, that pressure feed is usually GN2 or a similar inert gas. Um, and you can see the pressure range there. So uh, in addition, these thrusters are also sometimes referred to as warm gas thrusters. The reason is you can see that combustion temperature range there. It's still very hot, but hot gas thrusters are usually bipropellant thrusters because they have a much higher combustion temperature. And because of that, they usually have better performance in terms of thrust and ISP. So here's a schematic of a monopropellant thruster. The propellant tank is outside of the schematic, but the pressure feed system pushes the propellant through the propellant line into that injector assembly. Once it goes through the injector assembly, it gets pushed. The propellant gets pushed through the catalyst bed, which is this kind of bed of granules that I'll talk about later that chemically decompose the fuel. And so you can see the materials that are typically used for these warm gas thrusters. And it's important to note that the thrust chamber and the nozzle are radiation cooled. What this means is these materials are designed so that when it gets hot, they glow and they release heat energy through radiation. So now a common fuel that's been being used since the 1960s is hydrazine. You can see the chemical formula right there, N2H4. Um, it's good because it's very stable and can be stored for years on end inside these spacecraft. Um, the big downsides, number one, it's very toxic. And this creates a lot of headaches with fueling spacecraft or just having a robust design to detect leaks or just costly procedures. Another downside is the freezing point. So water's freezing point obviously is 32 degrees Fahrenheit, and this is even greater than that. So in space, you have to constantly be heating these propellant tanks to keep the hydrazine from freezing. So you can also see the compatible materials down there. Hydrazine is pretty good with most materials. Monopropellant hydrazine is a little bit different than the general hydrazine in that it's designed to decompose in the presence of a solid catalyst. Um, so in this case, you can see the chemical reaction right there. N2H4 is the hydrazine, NH3 is ammonia, and then you got some extra combustion gases in the products right there. X stands for the degree of ammonia decomposition. And when engineers are designing these thrusters, they want to decrease X. Um, and the reason why is you can see in the graph to the right, as X increases, which is on the X axis, the specific impulse, so if you look 3 charts from the bottom up, the specific impulse decreases as X increases. So they want the hydrazine to decompose directly into ammonia, and they want it to stay as ammonia and not decompose into other gases. So now looking at the types of catalysts, these are solid catalysts, and they're usually in form of granules. So on the right, you can see Shell 405 is the trade name for iridium and aluminum. And the different granule sizes. So usually they're arranged so that the fuel starts with the small granules and goes to the larger granules. This catalyst is effective at room temperature. So there's catalyst bed heaters in these thrusters that maintain that room temperature. But it's not like the materials down below where you have to keep these at a very hot temperature to keep that effective catalyst. So now I'm going to talk about the Aerojet Rocketdyne thrusters that use this new fuel. So here's the thrusters. These are small little guys. The GR1 is 1 Newton thrust, so conversion to pounds force. There it is. Same thing with the GR22. And their fuel is this new green propellant. But now here's a table of the performance parameters. So you can see the thrust range for that given feed pressure of the propellant tank. You can see the nozzle expansion ratio for both of those. Valve power, so different powers, and then you can see the specific impulse for both of those as well. So this new fuel is green propellant. It's AFM315E. It's the alternative to monopropellant hydrazine. In 1998, the U.S. Air Force Research Labs developed this down in Edwards Air Force Base. So it's an ionic liquid. And you can see right here the performance parameters relative to hydrazine. So it's both more dense and it has a higher ISP for this given thruster. So the other key thing to note is it uses similar catalysts to monopropellant hydrazine. Um, and there's been some reports of the catalyst having to be at higher temperatures um, than the case with hydrazine, but it's still under development. So the benefits, there's a couple of huge benefits. Number one, it's a lot less toxic than hydrazine. So on the right, you can see this lady from Aerojet Rocketdyne handling this propellant, whereas with hydrazine, they would have to be wearing skate suits, um, which are a lot more costly. And there's different costly procedures of handling hydrazine. So overall, the toxicity means a lot less costs in the process of fueling. Um, Next, the lower minimum temperature threshold. So because it's an ionic liquid, there's no really, I guess the freezing temperature of this ionic liquid is so low that they don't have to worry about it in outer space. So you wouldn't have to heat your propellant tanks constantly. Finally, this ionic liquid is even more stable than um, hydrazine in terms of adiabatic compression. Um, so that's another benefit. Looking at the drawbacks quick. Number one, and this is a big one, the propellant contains nitric acid. So trying to find materials that are compatible with this is really tough. And design engineers at Aerojet Rocketdyne are constantly looking for materials that can be exposed to this for a long time, because these spacecraft missions have to be out there for a long time, 15 years, and so finding compatible materials with an acidic materials is tough. Number two, the propellant acts as both a reducing agent and an oxidizing agent. So if you remember from chemistry, this causes corrosion um, with almost every metal. So that's another problem. So now I'm going to talk about the GPIM mission, which uses these thrusters to demonstrate the technology. So here's the assembly that Aerojet Rocketdyne co-designed with Ball Aerospace. Um, it uses 5 thrusters, and you can see the propellant tank in the middle. Um, Again, it's to demonstrate this new green propulsion technology. So here's a schematic of the system. It uses a blowdown pressure feed system. So you can see the GN2 and the AFM315E propellant. And when it was first launched, the fuel mass was around 14 to 15 kilograms. And um, through use, it gets blown down to 5 thrusters. So you can see 4 GR1 thrusters and then 1 GR22 thruster. The GR1 thrusters are used for rotation of the satellite, and the GR22 thruster is used for longitudinal movement. So the GPIM mission, here's the quick timeline. In June, the GPIM satellite was launched on a SpaceX Falcon Heavy rocket. About a week later, it fired up the 5 thrusters and it was successful. And then recently, about a month ago in October, NASA announced that they deorbited the satellite safely with pretty much an empty propellant tank. So now for the next steps of green propulsion, this next satellite developed by NASA JPL is a lunar flashlight satellite that's expected to fly on the Artemis 1 mission, which is expected to launch in November 2021. And this is a series of moon missions that is going to be happening in the next decade or so, assuming nothing gets canceled. And it uses this green propulsion technology to fuel the thrusters. So it's exciting stuff. And if you have any questions about this, feel free to reply in the comments in this discussion. Thank you for watching.